which the specks seem to move. When we do, we obtain beautiful sine curves. The natural way to generate a sine curve is to observe uniform motion sideways on. So Galileo inferred that Cosmos stars go round Jupiter in circles, in the plane of the ecliptic. Improved telescopes revealed that most planets in the solar system have moons. Mercury and Venus are the sole exceptions. We've got one, Mars has two, Jupiter has at least 67, Saturn at least 62 plus hundreds of moonlets, Uranus 27, and Neptune 14. Pluto has 5. The satellites range from small irregular rocks to nearly solenoids big enough to be small planets. Their surfaces can be mainly rock, ice, soil. Mars's tiny moons Phobos and Deimos race across the Martian sky, and Phobos is so close that it moves in the opposite direction to Deimos. Both bodies are irregular, probably captured asteroids, or possibly a captured asteroid with a duck shape 7P, recently shown to be two bodies that came gently together and stuck. If so, the one that Mars captured came unstuck again because of the planet's gravity. Phobos is one piece and Deimos the other. Some moons seem totally dead. Others are active. Saturn's moon Enceladus produces towering ice geysers 500 kilometers high. Jupiter's moon Io has a sulfurous surface and at least two active volcanoes, Loki and Pele, spewing out sulfur compounds. There must be huge subsurface reservoirs of liquid sulfur, and the energy to heat it probably comes from gravitational squeeze. Saturn's moon Titan has a methane atmosphere, much denser than it ought to be. Neptune's moon Triton is going round the planet the wrong way, indicating that it was captured. It's spiraling slowly inwards, and 3.6 billion years from now, it will break up when it hits the Roche. The moons of the larger planets often exhibit resonances. For example, Europa has twice the period of Io, and Ganymede has twice the period of Europa, hence 4 times that of Io. Resonances come from the dynamics of bodies obeying Newton's law of gravity. Planets with ring systems slowly accrete moons at the edge of the rings, and then spit them out one by one, like water dripping from a tap. There are mathematical regularities in this process. Various lines of evidence, some mathematical, indicate that several icy moons have underground oceans, melted by tidal forces. At least one contains more water than all Earth's oceans combined. The presence of liquid water makes them potential habitats for simple Earth-like life forms. And Titan's unusual chemistry might make it a potential habitat for un-Earth-like life forms. At least one asteroid has a very tiny moon of its own, Ida, orbited by diminutive Dactyl. Moons are fascinating, a playground for gravitational modeling and scientific speculation of all kinds. And it all goes back to Galileo and Cosmos stars. Please pause your audiobook and refer to the photograph with the caption, Asteroid Ida, left, and its moon, Dactyl, right. In 1612, when Galileo had determined the orbital periods of Cosmos stars, he suggested that sufficiently accurate tables of their motion would provide a clock in the sky, solving the longitude problem in navigation. At that time, navigators could estimate their latitude by observing the sun, though accurate instruments like the sextant were far in the future. But longitude relied on dead reckoning, educated guesswork. The main practical issue was to make observations from the deck of a ship as it tossed on the waves, and he worked on 2 devices for stabilizing a telescope. The method was used on land, but not at sea. John Harrison famously solved the longitude problem with his series of very accurate chronometers, eventually being awarded prize money in 1773. Jupiter's moons presented astronomers with a celestial laboratory, allowing them to observe systems of several bodies. They tabulated their movements and attempted to explain and predict them theoretically. One way to obtain precise measurements is to observe a transit of a moon across the face of the planet, because the start and end of a transit are well-defined events. Eclipses, where the moon goes behind the planet, are similarly well-defined. Giovanni Hedera said as much in 1656, and a decade or so later, Cassini began a lengthy series of systematic observations, noting other coincidences, such as conjunctions, in which two of the moons appear to be aligned. To his surprise, the transit times didn't seem consistent with the moons moving in regular, repetitive orbits. The Danish astronomer Ole Rømer took up Galileo's suggestion about longitude, and in 1671 he and Jean Picard observed 140 eclipses of Io from Uraniborg, near Copenhagen, while Cassini did the same thing from Paris. Comparing the timings, they calculated the difference between the two longitudes of those two locations. Cassini had already noticed some peculiarities in the observations and wondered whether they resulted from light having a finite speed. Behind all the observations, and discovered that the time between successive eclipses became shorter when Earth was closer to Jupiter, and longer when it was further away. In 1676, he informed the Academy of Sciences of the reason. Light seems to take about 10 to 11 minutes to cross a distance equal to the radius of the terrestrial orbit. This figure relied on some careful geometry, but the observations were inaccurate. The modern value is 8 minutes 12 seconds. Rømer never published his results as a formal paper, but the lecture was summarized badly by an unknown reporter. Scientists didn't accept that light has a finite speed until 1727. Despite the irregularities, Cassini never observed a triple conjunction of the inner moons Io, Europa, and Ganymede, all three of them aligning simultaneously, so something must prevent this. Their orbital periods are roughly in the ratio of 1 to 2 to 4. And in 1743, Per Workington, director of the Stockholm Observatory, showed that this relationship becomes astonishingly accurate if it's interpreted correctly. Measuring their positions as angles relative to a fixed radius, he discovered a remarkable relation. Angle for Io minus 3 times angle for Europa plus 2 times angle for Ganymede equals 100 exactly over long periods of time, despite the irregularities in the three moons' orbits. A triple conjunction requires the three angles to be equal, but if they are, the left-hand side of this equation is 0 degrees, as the relationship holds good. Workington stated that it wouldn't happen for at least 1.3 million years. The equation also implies a specific pattern to conjunctions of these moons, which occur in a repeating cycle. Europa with Ganymede, Io with Ganymede, Io with Europa, Io with Ganymede, Io with Europa, Io with Ganymede. Please pause your audiobook and refer to the illustration with the caption, Successive Conjunctions of the Three Innermost Moons of Jupiter, Io, Europa, and Ganymede, reading outwards. Laplace decided that Workington's formula couldn't be coincidence, so there must be a dynamical reason. In 1784, he deduced the formula from Newton's law of gravitation. His calculations imply that over long periods, the combination of angles concerned does not remain exactly at 180 degrees. Instead, it librates, oscillates slowly either side of that value by less than 1 degree. This is small enough to prevent a triple conjunction. He predicted the period of this oscillation to be 2,270 days. The observed figure today is 2,071 days. Not bad. In his honor, the relationship between the three angles is called the Laplace resonance. His success was a significant confirmation of Newton's law. We now know why the transit times are irregular. Jupiter's gravity causes the approximately elliptical orbits of its moons to precess Mercury's orbit round the Sun, so that the position of Perigove, the closest approach to Jupiter, changes quite fast. In the Laplace resonance formula, these precessions cancel out, but they have a strong effect on individual transits. Any similar relationship is also called a Laplace resonance. The star Gliese 876 has a system of the first being found in 1998. 4 are now known, and 3 of them, Gliese 876c, Gliese 876b, and Gliese 876e, have orbital periods of 30.008, 61.116, and 124.26 days, suspiciously close to ratios 1 to 2 to 4. In 2010, Eugenio Rivera and colleagues showed that in this case, the relationship is angle for 876c minus 3 times angle for 876b plus 2 times angle for 876e equals 0 degrees. But the sum librates around 0 degrees by as much as 40 degrees, a far bigger oscillation. Now triple conjunctions are possible, and near triple conjunctions occur once for every revolution of the outermost planet. Simulations indicate that the oscillation around 0 degrees should be chaotic, with an approximate period of about 10 years. 3 of Pluto's moons, Nix, Styx, and Hydra, exhibit a Laplace-like resonance, but this one has mean period ratios 18 to 22 to 33, and mean orbital ratios 11 to 9 to 6. The equation is now 3 times angle for Styx minus 5 times angle for Nix plus 2 times angle for Hydra equals 180 degrees. Triple conjunctions are impossible by the same reasoning as for the Jovian. There are 5 Styx-Hydra conjunctions and 3 Nix-Hydra conjunctions for every 2 Styx-Nix conjunctions. Europa, Ganymede, and Callisto all have icy surfaces. Several lines of evidence indicate that all 3 of them have oceans of liquid water beneath the ice. The first moon to be such an ocean was Europa. Some heat source is needed to melt the ice. Tidal forces from Jupiter squeeze Europa repeatedly, but resonances with Io and Ganymede prevent it escaping by changing orbit. The squeezing heats the core of the moon, and calculations suggest that the amount of heat is enough to melt much of the ice. Since the surface is solid ice, the liquid water must be deeper down, probably forming a thick spherical shell. As further support, the surface is extensively cracked, with a few signs of craters. The most likely explanation is that the ice forms a thick layer floating on the ocean. Jupiter's strong magnetic field induces a weaker one in Europa, and when the Galileo orbiter measured Europa's magnetic field, mathematical analysis suggested that a substantial mass of conducting material must lie under Europa's ice. The most plausible substance, given the data, is salty water. Europa's surface has a number of regions of chaos terrain, where the ice is very irregular and jumbled. One such is Connemara chaos, which appears to be formed from innumerable ice rafts that have been broken and moved. Others are Aran, Marius, Narbeth, and Rathmore chaos. Similar formations occur on Earth in pack ice, floating on the sea when a thaw sets in. In 2011, a team led by Brittany Schmidt explained that chaotic terrain forms when ice sheets lying above lens-shaped lakes of liquid water collapse. These lakes are nearer the surface than the ocean itself, perhaps only 3 kilometers underground. A depression of this kind, called Theramacula, has an underlying lake with as much water as the North American Great Lakes. Europa's lenticular lakes are closer to the surface than the main ocean. The best estimates right now are that aside from such lakes, the outer layer of ice is about 10 to 30 kilometers thick, and the ocean is 100 kilometers deep. If so, Europa's ocean has twice the volume of all of Earth's oceans combined. Based on similar evidence, Ganymede and Callisto also have subsurface oceans. Ganymede's outer layer of ice is thicker, about 150 kilometers, and the ocean beneath is again about 100 kilometers deep. Callisto's ocean probably lies the same distance under the ice, with an ocean 50 to 200 kilometers deep. All of these figures are speculative, and differences in the chemistry, such as the presence of ammonia, would change them significantly. Please pause your audiobook and refer to the photograph labeled